Hey everyone, so we just finished talking about Newton's first law, where an object in motion tends to stay in motion, an object at rest tends to stay at rest unless acted upon by an unbalanced force. And we talked about how the key takeaway is that if an object's in equilibrium, it's either going to be at rest or constant velocity. If the object has a net force, however, it's going to end up accelerating. We just kind of left it off there, but Newton's second law is actually takes this a little bit further and talks about, well, how is it going to accelerate? Is there what is the relationship between the net force and the acceleration? So the basic law is that the relationship between the net force and the acceleration, there's a direct relationship between them, and that there's an inverse relationship between mass and acceleration. Uh, but in particular, what's really important is that we end up getting this equation, F net equals ma. So we can use this equation to figure out the acceleration based off of the net force of the scenario, or vice versa. If we know what the acceleration is, we can figure out what the net force has to be. So um, this sometimes gets called the law of FMA. And like I said, it really just tells us how much we accelerate based off of the force. Now, I have to make this really quick aside. This is because of the AP. They'll always they've been asking this as a single question in the multiple choice. You just need to be aware that there's two types of masses, and the two types of masses come from the equations we use. So if we end up using this equation, F net equals ma, in order to find the mass of an object by basically measuring an acceleration and then measuring a net force and using that, then we end up getting what's called the inertial mass. So if we use this equation or anything derived from this equation, we're finding the inertial mass. Now there's a slight variation to this equation that we can also have. If we think about an object in free fall, we know accelerates at the rate of the acceleration of gravity, uh, 10 meters per second squared, or 9.8 if you want to be particular. And if we look at the forces acting on an object in free fall, we know that there's only one force acting on it, Fg. So by knowing that the net force is equal to this force due to gravity, and knowing that the acceleration is the acceleration due to gravity, I can rewrite the F net equals ma equation into an equation for how much force we feel on a planet. So if we want to figure out the weight or the force of gravity on a planet, we could use this equation, Fg equals mg. It just follows the same F net equals ma equation. If we use this equation to find mass, then we end up getting something called the gravitational mass. So depending on which of these two equations we use, we end up getting a different mass. Now, the reason why this is important is because the questions that they ask, like I said, there's only going to be one question, but the way the question gets asked is essentially which of these experiments or which of these methods would give you inertial mass, or which one would give you gravitational mass, something like that. And the idea is that you want to realize, you want to be aware of what equations and what experiment you're doing, what equation you end up using, and whether or not that's getting you the inertial or gravitational. One of the things I always tell people, because sometimes there's some experiments that it can be a little tricky whether they use F net equals ma or Fg equals mg. Like I said, this also pertains to equations derived from these two equations. So another way to put this is that if you're doing an experiment that has to be done on Earth, not that it is done on Earth, but that it has to be done on Earth where there's gravity, or some other planet that has gravity, then that experiment's going to find gravitational mass. If we instead are doing it in a setup where we don't need gravity, we could do it in the ISS space station, then we end up getting inertial mass. A perfect example of this is, let's say I took a balance beam. I get a beam where there's a tray on two ends, and I place masses on the two ends. Now, It may not seem like I'm using Fg equals mg because I'm really just saying I'm comparing the mass of this to the mass on the other side that we know. But that does, in fact, use gravity, because if it wasn't for gravity, those objects wouldn't push down on the two trays, they'd float there. So we would need gravity in order to use a balance beam or any sort of balancing setup. Likewise, if I use a mass on a spring, there's a way to use that to find the mass. That can be done in space. We can easily attach things to springs, and the spring provides the force. We don't need gravity in that case. So that experiment would find inertial mass. Now I know what you're thinking. What's the difference? There is none. As far as we know, there's no measurable difference between inertial mass and gravitational mass. Scientists, physicists believe that there should be a difference because of the definition of these equations not technically being the same. That gravity is basically its own bag of worms. So there should be a difference between these two, but as far as we found, there's nothing. So the question is, why do we even care if there's no difference in them? Honestly, I don't know. Like I said, it's something that gets brought up on the AP every year, so I want to put it in there to make sure that you have it. It's a really easy question to get right, and you don't need that many to get right in order to get a 3 or 4 or 5 on the AP. So any single question can help. All right. So here are two questions. Pause the video, work yourself. I'm going to go over in a second. All right. So here, the first question wants us to figure out the net force. So I use the equation F net equals ma, plug the numbers in, and I get 2,300 newtons. Easy enough. The next question, they want to find the weight. So again, looks like I don't have enough information, but again, the weight is the Fg, so I'm using Fg equals mg. I know what g is, that's 10, because we're on the Earth. It doesn't say that we're not on the Earth, so I can assume it. So I plug the numbers in, and I get 1,000 newtons. All right, here are the next two questions. Pause the video, work yourself, and we'll go over in a second. All right, so for the first one, they want us to find the acceleration. Again, easy enough. F net equals ma, plug the numbers in, blah, blah, blah. We get acceleration is 20 meters per second squared. Honestly, by the end of this, you should have a very strong connection between force and acceleration. Your mind should immediately go to this equation the moment you see these two words, anywhere near each other. For the next one, this time they're giving us two forces, so I have to go back to what F net actually means. F net means the sum of the forces. So I have two forces. I have a force going to the right. Let me just pull out a pen. I have a 50 Newton force to the right. I have a 28 Newton force to the left. So my net force, because they're in opposite directions, is going to be the difference of that. I'm going to use 22 newtons as my net force. So when I plug the numbers in, I get 1.1 meters per second squared. I might want to include the direction, since I do not have directions in this one. So this would actually be to the right, because the acceleration of the force will always go in the same direction. Now, before I continue, I just want to make one quick comment. You don't normally see the equation written like this on the reference table. First, you see it more in a fractional form like this, F net divided by mass. Personally, I just like writing it like this. It makes it a little bit easier. I find that a lot of people can make mistakes when you have numbers in the denominator like this and you're solving for mass. So I just like it written out flat like that. But the other thing that I want to point out is that instead of writing it as F net, you will sometimes see it written like this. This means the same thing. This just says that the sum of the forces, which again is the definition of what a net force is. So just throwing that out there, that if you're looking for this specific equation on the reference table, you're not going to see it this way. It's going to be in a slightly different way, but it all ends up being the same thing. All right, here's the next question. Pause the video, work yourself, and we'll go over in a second. All right, so they want us to figure out the which one represents the force exerted on the block by the table. Now, this is actually pretty easy. I can get rid of two of these choices because they make no sense. 3 and 2, because they're both in kilograms. Force is not measured in kilograms. There, it is measured in newtons. Now I can do some calculations, but for the most part, they're looking for the force exerted on the block by the table. That means it's looking for a normal force. We know that when an object's on a table, the normal force always pushes it upwards. So, choice 1 is my normal force. It is the only one that actually has the arrow going up, measured in newtons. I could do the math to figure out why it's 49.1. I'll do it quickly. Fg pulls down. We know that Fg equals mg, so I can take the 5 times it by 9.8 to get 50 newtons. Because the table is at rest, or sorry, not the table, the block is at rest, we know that the object's in equilibrium. So if the bottom is 50, the top is 50. So right here, you can already see how Newton's first two laws interact with each other. You're going to be constantly going back and forth between the equations F net equals ma, Fg equals mg, and the idea of equilibrium in order to figure out what forces are. All right, here's the next question. Pause the video, work itself. I'm going to go over a second. Now, some of you may have caught on to this, but this is actually a fairly tricky question. It's not tough at all, but it's tricky because a lot of people will mistakenly use that acceleration of gravity that's provided. That number is a red herring. The actual answer is 98 kilograms, because if you remember from previous science classes, mass never changes. It doesn't matter what your mass is on the Earth, it doesn't matter what the acceleration of gravity is on the moon versus the Earth. If your mass is 98 on the Earth, it is 98 everywhere in the universe. The only way you can ever change your mass is by literally chopping off a piece of your arm. So the mass never changes. Also leads me to want to remind you that mass and weight are two different things. Um, Through society, the way we use the word mass and weight is very interchangeable. You'll see that all the time, that people use the term mass as just another way of saying weight. But you have to remember that that's not the case here. That mass and weight are two strictly different things. Mass is how much matter you have. Weight is how much you're affected by a planet. Right? Here's I think this should be the last question, so pause the video, work itself. I'm going to go over in a second. All right. So at first, it may seem like you don't really know where to start. Now, one thing I had mentioned in some previous topics is that like you typically want to write down everything that's given to you, and you kind of want to do the same thing here, except instead of writing it down like in a chart or just off to the side of like A equals this, B equals this, you're writing it down in the form of an FBD. So what I can do is I could draw an FBD of this. I already have these two forces. I can add in the FG force and the FN force. And basically what I'd recommend is start calculating whatever you can. For example, since I know I have the mass here, I actually can find Fg. I know that Fg equals mg. This is going to be 4 times 10, or 40 newtons. I also know that the Fn, because it's only accelerating horizontally, I know that these two forces are balanced. So this normal force is also going to be 40 newtons. But unfortunately, that's not really going to help me in this specific case. It could have helped me maybe in the future, but for now, it's not really useful. So what else can I find? Well, they give me an acceleration, so I can use that instead. I know that there's an equation F net equals ma that uses this acceleration. So I have 4 times 10, which is also serendipitously 40. So now I have a lot of information, and the question is, well, what can I do? Well, if I go back, now that I know what the net force is, I can take advantage of the other unofficial equation, if you will, or the definition of what a net force is. The net force is the sum of the forces. Since the object is accelerating horizontally, basically what this is saying is that this force is what I get when I take this number and this force and add it to this force. So I can use that to set up my equation. So I get F net equals the applied force minus the friction. I'm subtracting them because of the fact that I know friction is going to the opposite direction. I plug my known numbers in, and I get that the frictional force is 10 newtons. Now, there's a few other things that I want to point out to this because this question actually perfectly illustrates some things that I really want you to make sure that you do as far as setting up your problems. Like I said, when you're drawing I don't want that one. When you're drawing an FBD for yourself, or sorry, I should rephrase that. If you're drawing an FBD for a grader like me, you are not including anything more than just the forces acting on it. So the FBD that I drew before, where I drew gravity and the normal force, I would leave that as is, and I wouldn't touch anything else. But when you're drawing the FBD for yourself, one of my recommendations is to include this, an arrow off to the side that shows the direction of acceleration. The reason I recommend doing this is because in later, more complex problems, you're going to use this for sign convention. Now, what I mean by this is that in the previous topics that we've done, the kinematics, we pretty much said that anything going up and to the right is positive, everything else is going to be negative. But in a case like this, maybe not so much right now, but in the cases that we're going to talk about later on, um, saying that something to the right is positive and something going to the left is negative isn't really going to be useful. So instead, what we're actually going to do is say that the direction that the acceleration is going to be defined as positive. This makes it so that our net force will always be positive, and we at least don't have to worry about the signs there. There's a few things to note is that if the acceleration was going to the left, the way I'd set up the equation, trying to find the way I'd find the equation is by doing F net equals, we would say that the acceleration to the left, it's the frictional force that's now positive, minus F applied. If we didn't know which one was going to be positive or negative, we actually could have also left it as positive and got the negative later on. But this is the thing that I want you to start doing from now on is including the direction of acceleration, and that way when we do essentially this, the setting up the equation for F net, stating which one is positive, which one is negative, um, doing that so in a way where whatever direction we had drawn the acceleration, that is being defined as the direction positive. And that's pretty much it. There's one last law that we have to talk about. We'll talk about it later on. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.